I'm Puzhao, and I will introduce our F3, the fault forecasting framework for cloud systems. The motivation for our project is to empower the large-scale distributed systems, such as Azure, Office, to achieve higher availability and reliability. We aim to predict the cloud failures, such as disk failure, node interruption, high latency, and so on, so that proactive actions can be taken to avoid negative impact. And the action include lab migration, failover, reboot. As we aim to predict a component in cloud system whether will fail in the near future, we formulate this task as a binary classification problem. The input is the component, its own historical data and its contextual data. And then through our F3, we adopt the failure probability. For example, in the disk failure prediction scenario, we want to predict whether a disk will fail. The input includes the disk's own signal, such as its historical smart data, and the contextual information, such as neighboring signals and system signals. There are many challenges in this scenario which makes this work very difficult. We select 3 major challenges as shown. The first one is the extremely imbalance. It's well known that the number of the healthy samples is much larger than that of the failed ones. In many failure prediction scenarios, the ratio can reach 1 to thousands, which is really challenging. The second one is the complex running environment. Because there are many components in the cloud system, such as disk, memory, CPU, and so on, they work together and interact with each other, which makes it very difficult to make full use of the complex context information. And the third one is the inconsistent data quality. This problem is very practical, but easily gets ignored. That is, in the online situation, some signal values are unavailable because of data delay and data missing. But days later, the missing value have been filled. Then, when we collect the historical data, we will get the filled data with good quality, which is quite different from the actual online situation. When we using the good quality data train model and put the model to the online, the model performance will not go as we expect. So this problem makes the model not robust and easy to overfitting. Our approach contains 2 aspects, the model and the data processing. The model mainly includes NAM, the neighbor-aware attention model, which is the key model of our approach. For the data processing, our approach contains 2 practical and innovative mechanisms, the temporal progressive sampling and data masking. Different from the existing models in failure prediction area, our NAM includes the neighbor-aware component, which uses to capture the contextual information. For example, in the disk failure prediction scenario, the neighbor-aware layer not only encodes the disk itself information, but also can make use of its neighboring information, such as the other disks on the same node, the driver information, the OS information, and so on. And this can benefit the complex running environment challenge. Besides the neighbor-aware component, our NAM contains a state-of-the-art temporal information encoder and is a attention-based layer, so it's faster than RSTM and GIU, and has a better ability to capture long dependencies. To address the extremely imbalanced challenge, we employ TPS as cost-sensitive. First, we named the period between prediction occurs and failure occurs as leading time. For each failed component, we use different leading time to generate multiple positive samples. In this way, we can get more positive samples. And also, we can let the model learn more failure patterns. Besides the TPS, we also employ cost-sensitive loss to address the extremely imbalanced challenge, as other state-of-the-art approaches do. It can weight the penalty of positive and negative samples. This aims to solve the inconsistent data quality challenge, to make the model more robust and make the model insensitive to individual feature and individual data. For the training data, we mask some values to mimic the online situation. While for the model, we add job part. To evaluate the effectiveness of our approach, we select the most popular and typical scenario, the disk failure prediction. First, we collected two datasets from about 9 million disks in Azure. Then we compare our NUM to 9 state-of-the-art competitors. And we can learn from the table our NUM can outperform TCNN, RSTM, and GBDT by 7, 8, and 12% in F1 score. At the end, our approach has been transferred to Azure Compute and M365 and achieved business impact. For next step, we plan to extend collaboration and deep dive research. Thank you.